Hello everyone. Today we are going to be talking about Chapter 13, Forces in Fluids. One of the things that we need to talk about with forces in fluids is a word called pressure. And pressure has a formula. It takes something's force, so that could be weight, it could be newtons, over a given area, and that will give you a value. So if you've ever been pig piled upon, if you have just one or two people, you feel a little bit of pressure, but if you have 10 people on you, you feel a lot of pressure. We see this with air, with liquid, and a lot of other examples of pressure that we're going to discuss in this PowerPoint. So first, let's talk about water pressure. Water pressure, the deeper that you go, the more pressure there is. The reason for that is it's not just the pressure of the direct water around you, but it's the air that's also above you. So when we go, for example, to the deep end of the pool, we will sometimes feel a little bit of pressure on our ears. And the reason for that is because there's more water pushing on our eardrum. If we stay close to the surface, there's less water that's pushing on our ear, so we don't have that be as painful. If we look at some of the diagrams, submarines have to be built in such a way to withstand a lot of that water pressure, and they can only go to certain depths before they have, for example, some of their metal start to kink or bend because of that water pressure. Something kind of unique is if you were to take an egg and drop it into water and let it sink and sink and sink and sink and sink, eventually it would actually implode, meaning that the pressure from the water would squeeze it in. And it's kind of a unique thing that happens because of that water pressure. Not only do we see pressure in water, but also in air. And so when you're at sea level, there's more air that's around you and pushing down on you. Now, air isn't very heavy, so we don't feel that weight very much on our shoulders. But in some planets, with the type of gases that they have, their air would feel heavier because of the type and the amount that they have. One of the other examples of this in real life is Olympic long distance runners will oftentimes go to higher elevations to train. And the reason for that is because they are training their bodies to literally run with less oxygen. That way, when they come down to sea level, it is much easier for their body to run that 26.2 mile or that long distance mile because they have trained on less oxygen. When it's at sea level, there is more air, as this diagram is showing us. Those of you that have ever been on a jet or a plane, in their safety instructions, they talk a lot about if the cabin loses pressure. Well, what that means is air is less dense the higher you go up. And so what would actually happen is if there was like a hole in the plane, air from inside the plane or jet would go out and it would try to equalize the pressure. And so that's why those masks would drop down and you would want to have that oxygen mask to breathe. We also see this in an example with balloons. When we let a balloon go out, it makes that tooting sound as it flies around. The reason for that is because the air pressure is higher inside the balloon than the outside, and that air is wanting to escape and equalize. Not only do we talk about air pressure with flight and, in our case, exercise, but also we can talk about it with our weather. So when we look at a weather map, sometimes we'll see a big red H or a big blue L, and that does not stand for high temperature and low temperature. Instead, it stands for high pressure versus low pressure systems. And there's a tool over on the right here called a barometer that can measure in a variety of different values. But what we look at is the lower the pressure. So for example, let's say it was in the 28.5-ish range, that is more likely to bring about cloudy weather or rainy weather. If you have a high pressure system, those molecules are literally tightly packed and they kind of scurry away any of the other air pressure near it, and it brings about clear days. Not necessarily hot or warm, but it does bring about clear days. In the diagrams, what you're seeing is what happens with low pressure is some of that moisture from the ground will actually go up because of evaporation. We're in a high pressure system, again, because that air is so tightly packed, it keeps those molecules down. And so there's evaporation, but not as much of it goes into actually making up those clouds. Now, let's talk about structural pressure. So what makes a bridge sturdy? What makes a structure sturdy? there's a lot of physics and there's a lot of engineering that goes into making bridges and other structures very, very secure. And one of the things that we look at with bridges, and we looked at this with our experiment, or if you've looked at doing this with toothpicks or with popsicle sticks, one of the main things that you need to worry about with making a bridge are those support beams, as you're seeing in the picture in the top left. Those are what are going to hold on to the majority of the mass or of the force of vehicles or people that are crossing that bridge. The structure support, for example, these beams, when they're possible, really help out with supporting a lot of that force. So the more vertical beams you have, that means that the more weight that it can bear. But what if you have a bridge where there's a huge long distance that's going on? Well, one of the things that we see is a lot of support, but also we see a lot of angles in bridges, and we'll look at that momentarily. When we look at a structure like this, like what we see in the Golden Gate Bridge, and then there's a couple in like Boston, these are cable bridges. And so what they're doing is they not only have the structural support or beams, but then they also have vertical support where those beams are holding up segments of those beams, segments of cement, mortar, that sort of thing, in order to withstand more force. And when we see things that are above light cables, that's beneficial. When we see things like a truss, but the vehicles are still going here, that's not necessarily going to help out the structure or support of the bridge as much. And specifically, we see this with our houses. And so if you've ever looked at a truss before, one of the big things that they try to do is they try to equally distribute the force that that object might be bearing. So in our roofs, you think about shingles and you think about the wood itself, there's quite a bit of mass to it, but then you start adding snow or rain or other things to the roof. And so one of the things that structurally we try to do is we try to triangulate things. So if we look at this truss and how it has a triangle to it, what it's doing is instead of having one straight beam having all the weight, it distributes that weight, making it so that these support beams are stronger. Now, yeah, does it have more wood used? Absolutely. But it does make it a lot more sturdy. So we can see this with all these different trusses that construction workers and engineers have come up with. But what they're trying to do is they're trying to equally disperse more of that weight, more of that force around so that things become more sturdy. So we see this a lot with our structural type of pressure. Going back a little bit to pressure in fluids. So a fluid, by definition, is a substance that takes the shape of its container. So if you take just a water bottle and you seal it up with no water in it, you're like, well, there's no fluid in there. Well, actually, air is a fluid. It's taking the shape of that. So if you squeeze that water bottle, you can, feel the pressure of that air. We see it more evidently when we actually have water in our water bottle, and the pressure that it receives or has changes. If we look at this diagram, if we were to take a water bottle, poke a hole at the top, the middle, and the top, yes, has water coming out, but it's not necessarily a very high force. It's just kind of leaking out. When we go to the bottom, notice how it's shooting out. The reason for that is not only is there pressure right near it, like it is on all of these openings, but this bottom one has the pressure of all of this water, all of this liquid pushing down, and thus making this force more. And so that's kind of a cool example of how pressure can change in a fluid. In air, remember, air is a fluid. We see this when we go at the bottom of the mountain or sea level. Here's our long distance runners training up here. There's less oxygen for them to take in, so they're training their body to run on less oxygen. So when they come down to sea level, it's much, much easier. Again, with air, we don't feel that as much. However, those of us that have been to, like, let's say, top of a mountain or higher elevation, you can sometimes feel that. Some people get lightheaded because they're not used to having less oxygen. Or even people that do an activity like walking, sometimes it can seem like it's somewhat labored because of that less air at higher elevations. So when we talk about liquids, let's stick with liquids here a little bit. One thing that we talked about is the particle model, where solids, they have particles that are more densely packed. Liquid, they're a little bit more spaced, and gas, they're super spaced. But within a liquid, we can change the density of that by changing its temperature. So we equated this: if you're a penguin and you're cold, what do you do in the middle of the winter? Well, you huddle together to preserve body heat. When we're hot, things start to spread out. So something that's kind of unique about water is that, usually we say the colder something is, the more dense it becomes. Water is actually most dense at 4 degrees Celsius, not 0 when it freezes, but 4 degrees Celsius. Water is kind of a unique substance in that it actually locks into a crystal structure. And so that's why water expands when it freezes. And that's why you have things like potholes and frost wedging that can take place. But what we're trying to say here is that when you heat or cool things down, it does change its density and it does change the pressure in that fluid. Next, we're going to talk about Pascal's principle. And what this means is that if you have a closed container, like what we're seeing in this water bottle with the orange dyed fluid, is that if there's pressure at any point, that pressure equally distributes itself all throughout that container. So there's no one spot that receives more or less pressure. We would see this if we pop the balloon in several different areas. We took a pin and we put it in several different areas. That air would leak out equally if given enough time. Speaking of that and pressure, we also use that to our advantage with different hydraulic systems. So a hydraulic system is something that uses pressurized fluid, in most cases it's air, to really change the force on certain things. So if you've ever wondered how or why garbage trucks work or how dump trucks can lift such high amounts of weight, it's because they actually use this idea of pressurized fluid to their advantage. And so with hydraulic systems, as you see in the diagram to the left, they're using machines and compressors and those types of things in order to generate more force and cause movement. Another principle that we need to talk about in this chapter is Bernoulli's. So we talked a little bit about how we get different types of flight. And what he said is as the speed of fluid increases, the pressure within the fluid decreases. So when we talk about how and why airplanes fly, the number one thing is that they fly because of what we call lift. In order to get lift, the wings are the main thing that are able to create that. So in the diagram, what you're seeing is on the red part, there is higher pressure at the bottom, making it so that it's forcing up on the wing. And when you have thrust, that's forward motion, it's able to generate more of that force, more of that lift, and that's something that we see with flight. We can see this in a smaller example with a whistle. So when we blow into a whistle, we're adding a lot of air, and then we're putting it through a really, really small space, and that's what actually creates the sound. Our next topic is what we call buoyancy. This is something's ability to force something to float, and by definition, ability of a fluid to exert an upwards force on an object. So we know that certain things can or cannot float, but we have to ask the question, well, why do some things float? Why don't some things float? Why are ships in the ocean so much bigger than ships that might be in Lake Superior, Lake Michigan, or the Great Lakes? And so buoyancy, what we look at with that is what that object is made out of. And another property that you have to talk about with buoyancy is density. So here you're seeing a density cup filled with a variety of different material. The stuff that is more dense is at the bottom. The stuff that is less dense is at the top. But what does that have to do with buoyancy? Well, if I ask you this question, would it be easier for a ship to float in honey or a ship to float in vegetable oil? The answer is honey. Why? Because it's more dense, it's more buoyant. It would force the ship upward. If I ask what would float better, water or corn syrup would make things float better because it itself is more dense and would push up on those things. And so within the ocean, one thing that we see is that the more salt water, the more saltier the water, the more dense it is. The less salty stuff is actually at the top, and that happens because of what's called a density gradient. And so with buoyancy, we go back, it's the ability of a fluid to exert an upwards force on an object. If it is more dense, it becomes more buoyant. If it is less dense, it will not be as buoyant. And so with buoyancy, we have to talk about density and what those objects are. That concludes our presentation on our chapter for today, Forces and Fluids. Have a good rest of your day.